Now we're going to do a brief lecture. I apologize again. I didn't get this lecture recorded. Okay. Yeah, I don't know what that means. Registration is being processed. Hopefully that just means that they've got a lot of people registering and it's taking time. But again, here's the thing, let me know if there are technical issues. And of course, understand that if, for example, none of us can get registered today, or there's some other huge issue, obviously the due dates would be changed. Okay. So I'm not going to let that affect your grades. Okay. Yeah. I mean, hopefully you work with me for a whole semester. Hopefully, that, I think the important thing is that you complete things. I put due dates on to get you, to motivate you, okay, but not to punish you, right? Okay, so let me, where is my, oh, I know where it is. Sorry. I hate it when people fumble around on their screen here. Okay, so I didn't have time to record this lecture in advance. So what I'm going to do is record the lecture now, okay? And I'll post it as a separate lecture, but if you just follow along, these notes are posted in Module 1. I don't know if you saw it, but they are posted. And so you'll be able to download them and print them, and then I'll actually post filled in ones. I don't have a lot of filling in, but I'm going to make some notations on these, okay? This is intended as a review. So it's not intended to replace what you did last semester. It's intended to just sort of remind you of things, clean up some edges, and then kick you into assignment, all right? Okay, first of all, I want to point out that there is also on the Mastering website, there is a reading assignment from our Wade textbook, Wade and Simek textbook. It's already posted. It's chapter 12. I believe I also posted it last semester. So again, this is what I was talking about. You get your access code for that book. It should be applicable the whole semester, whole year, okay? I do encourage you to do that reading, especially the last portion of the reading where they go through and they show examples of different types of IR spectra and what the peaks look like. You've already done this once, but you'll recall that there were some subtleties, like certain peaks are broad and some are sharp and so forth, okay? All righty, so let's talk about IR. Okay, so the IR is based on a simple principle, or explores a simple characteristic of bonds, and that's that bonds are not, they're not rigid, okay? What that means is that when we build our model kit, we build them with these plastic balls and then this plastic stick, right? And when we put those two atoms together, they look like, okay, here they are, they're this far apart, they're always this far apart, they're hard, that's like this hard, rigid thing, right? But that's actually not what bonds are like. Bonds are actually, one of the models we use, we talk about them acting like springs, but the main point is that the atoms are moving like this. We call that a vibration, okay? This particular one, where the distance between the atoms gets bigger and smaller, we call that a stretching vibration. There's also a vibration where if you have an atom, I'm sorry, this looks totally weird with my face on there. You have an atom, there's an angle between those bonds. That angle gets bigger and smaller, okay? That's called a bending vibration. And these are just natural things that occur, okay? So for example, what I want to show you is, if I have an atom, there's a bond between it, I have an atom, okay? And there's a distance between those two atoms, well, those atoms can be I don't know if that's exaggerated enough, but right? So I'm basically trying to show that they started here, they moved out to there, then they moved back in, right? That's a stretching vibration. Okay, there's also a vibration that looks like this. I'm going to really exaggerate this so you really see it, right? Where the angle sort of defined by 3 atoms, right? 2 bonds and 3 atoms gets bigger and smaller. This is a bending vibration. There's actually more than one type of bending vibration. This particular one is called scissoring. Just for completeness sake, in the full set of notes from last semester, I think I showed all of the different vibration types, but if you didn't see those, someday I can do it. But scissoring, because it looks like scissors, right? You're doing like that. Okay. Generally, I would say the most common type of vibration that we look at and interpret is a stretching vibration, but there are some useful bending vibrations if we get a little advanced in the IR. Okay. All righty. Now, here's the thing about these vibrations. So the vibrations are these cyclic processes. They go back and forth. And so we have a term to describe the speed of this cycle. Like, how long does it take to go from smallest to biggest and back to smallest? Okay. We call that the frequency. All right. We're going to talk about frequency again in a little bit. But the thing about the frequency, okay, is that the faster that frequency, the more energetic the vibration. Does that make sense? But there's another way that that vibration can be energetic. I'm sorry, I know that this is so weird in my face in the way here. But basically, if we go at the same speed, okay, but we go bigger. So it's the same speed, but it's bigger. That's called the amplitude. Okay? It's like the size of that vibration. And the bigger the amplitude, the more energy. Okay? So, molecular vibrations have a very interesting property. It's a property that's shared by almost all really, really tiny objects. And that is that, unlike us, where when we get in our car and we put the accelerator, we could go 41 miles per hour, we could go 41.1 miles per hour, 41.2 miles per hour, whatever. We have all these different speeds, basically any speed that we could go. Really, really tiny objects are restricted to only certain energies, only certain speeds or whatever, okay? So they might be able to go 20 miles per hour and 40 miles per hour and 60 miles per hour. And if they were to increase, they would go without even going any speed in between. They'd be going 20, and then all of a sudden they'd be going 40. Okay? We say that systems like that, where it's not continuous, right? Where there's only certain allowed values, we call those systems quantized. And that is one of the important characteristics of 20th century physics, right? Is they started studying quantized systems as opposed to 19th and 18th century physics, where they studied continuous systems, right? Where you had any allowable value. Okay, everybody cool with that? Quantization. Okay, so bond vibrations, molecular vibrations, are quantized. When you have a bond with two atoms and it's vibrating, it is only allowed to have certain energy values. And that is super useful to us. That's what allows us to do IR spectroscopy. Okay? So I have a picture here on my screen. This is a picture that I think, well, if any of you guys are chemistry or physics or engineering majors, you will see this again. The rest of you probably won't, okay? But I want to introduce it for those people who might see it again and give it an explanation so that maybe you'll kind of get it the next time you see it. It took me a long time to understand this. Didn't understand it the first time I ever saw it, okay? So here's what they're doing. They're showing a bond. So we have, an atom here, and then we have this distance D. That's, R, capital R, okay? How far apart are these two atoms? Okay? And it turns out when you take two atoms and you put them together, if you stretch them apart and then hold them there, their potential energy goes up. If you push them back to where you started, it might go down. But then if you try to push them too close together, the potential energy goes up again. All right? And so this basically represents the potential energy change, like when we take two atoms that are really far apart, okay, where R is very big, and then we start putting them together. So in fact, actually what I usually think of this as is one atom is right here, and then the other atom is moving in, and the distance here, this is R. Does that make sense? So think of one atom being fixed, you're moving the other atom. How far apart is it? Okay? Everybody cool with that? That's what the x-axis is. And then what we do is every time we move an atom, we measure the potential energy and we put a plot. And that's what this blue, I'm going to make it blue, what this blue curve is, right? It's how much energy does that have? Okay? Everybody good with that? If you have a question about that, speak up or whatever. Okay, so here's the deal. When we look at a normal bond has what we call a bond length. And the bond length is actually the average R of the atoms. In other words, the atoms don't have one fixed thing. They go kind of bigger, they go kind of smaller. So when we talk about a bond length, what we're saying is they go bigger and smaller, but on average, they're about here, right? That's in between the biggest and the smallest. Does that make sense? And that would be the lowest energy, the lowest potential energy that bond can have. But most bonds don't have that lowest energy. They have a little bit of extra potential energy, okay? And so what happens is, because they have a little bit more potential energy, there's like an amount of potential energy. They're going to start there. Then remember, potential energy often in physical systems gets converted to kinetic energy. So here's what happens. They're at this high potential energy. They start moving together, right? So as they're moving together, so they're starting out here. I'm going to put it really far, okay? They start moving, they move together, right? Until they're at that perfect bond distance. But when they're at that perfect bond distance, they've taken all that kinetic energy or potential energy, they've converted it to kinetic energy. So now they're at that perfect distance, but they're moving really fast, right? So they start here at the high energy, they're not moving. They start moving together, they're moving really fast. That means they move past that perfect distance. They move together, right? And as they move together, they start pushing each other apart, which slows them down, but increases their potential energy again until they get, again, to that same high potential energy they started with. There's no friction in this system, so energy is conserved, okay? And they stop moving. But now the potential energy pushes them apart, so they start moving again, right? And their energy goes down, and then they go back up like this. So I'm trying to use the height as sort of a representation of the potential energy, right? Do you see how they're doing that? They're moving from a wide distance to a narrow distance. That's what this graph is trying to show. Do you see? It's saying pick a potential energy level. That's the widest they're going to be. Now they start moving, they reach that thing, then they move up until they stop moving at the other end of that curve, right? And then they move back. So they're moving back and forth. Everybody cool with that? Okay, so here's the point. Remember, I told you they're only allowed to exist at certain potential energies. So this would be the lowest one. Then this is a potential energy. Then this is a potential energy. So what this means is they're going to vibrate between certain fixed allowed distances, but the speed of their vibration will be constant. And if we look then, what we have here, that distance there is a delta E, right? It's a change in energy. So I can have them vibrating this far apart. If I put in energy, now they start vibrating this far apart. Same speed, just wider, okay? That's the quantum effect. Now, the significance of that then is that to change that vibrational energy, we have to put in exactly the right amount of energy. Exactly delta E. If it's bigger than delta E and it doesn't match any of those distances, it won't be absorbed, just goes right through them. Okay? So what we're doing is increasing the amplitude of the vibrations. So bonds absorb IR radiation, causing a change in the amplitude of the vibration doesn't change the frequency. Okay, next. This is another review thing. When scientists started studying this, and they realized that bonds were not rigid, they were looking around for, then how can we explain what bonds are like? And they hit upon the idea that bonds are like the atoms are two balls, and the bond is like a spring connecting the atom. And this became known as the ball and spring model. Now, it's a model. In other words, it's something that we use to sort of represent reality, but it's not exactly reality, okay? So the atoms aren't really balls, and they're not connected by springs, okay? But they act like they are. And the thing is then, because they act like that, we can use analogy. Now, what does that mean? Well, what that means is if we were to actually take large physical balls and hook them up with springs and look at what causes them to vibrate, why do they vibrate bigger, what changes their frequency, things like that, we could say, well, these are the things that cause these balls and springs, you know, like these real balls and springs to do that. Maybe we have similar effects in the atoms. Does that make sense? And so there was a guy who actually studied this, super interesting scientist guy named Robert Hooke in England, was a contemporary of Isaac Newton, did a whole bunch of really cool and interesting stuff, including he was one of the first people to look at natural objects using a microscope And in fact, he published a book in 1664, something like that, called Micrographia, which was basically like the first biology book, where he looked at bugs and stuff and he drew really awesome pictures and everything. Anyway, super interesting guy, kind of a weird guy. At one point, he decided to study balls and springs. Okay. There was actually a reason. He was trying to figure out how to make a clock that would work on a boat because of issues in navigation. And there was like a huge prize available if he could do it. And he thought balls and springs might work. It didn't work out for him, but that's why he studied these things. Okay. So he came up with something called Hooke's law. Now, I'm not even going to write Hooke's law. You don't have to know Hooke's law. You don't have to know the formula. Okay. You're not doing calculations with it. All I want you to understand is that Hooke basically found that there were two important things when you were looking at balls and a spring. Okay. There were two important things that caused the spring to vibrate at a different frequency. Okay. That changed the frequency of the vibration. All right. The first thing was the mass of the balls. Okay. And basically, there's an inverse relationship. As the mass of the ball increases, the frequency decreases. So if you put heavier balls on an atom, the bond is going to vibrate more slowly. Okay? Little light atoms vibrate really fast. Okay? Everybody cool with that? So what I'm doing here is I'm correlating the mass of the balls with the mass of the atoms, right? The mass of the balls that Hooke measured, it's just like the mass of the atoms in our bond. So bonds with heavier atoms vibrate more slowly, in other words, at a lower frequency. The other thing that he found was you could take the spring and you could make it thicker. You could make it more stiff, harder to stretch, okay? And as the spring became harder to stretch, it would vibrate at a higher frequency. Okay? So again, the strength of the spring increases, the frequency increases. Okay? Now, what we can correlate that with is whether it's a single, double, or triple bond. So a single bond is a very stretchy, weak spring. A double bond is a little stiffer, right? A little harder to stretch. Triple bond is a really strong bond, very hard to stretch. Okay? In general, the stronger the bond, the stiffer the spring, if that makes sense. Okay? And so there's another effect we're going to talk about in a little bit. If we make that bond weaker, then it vibrates at a lower frequency, right? Weak bond, low frequency, strong bond, higher. So when we make it weaker, it vibrates at a different lower frequency than we would otherwise expect. Okay? Everybody cool with that? That's all you need to know about Hooke's law. Okay? Finally, then, there's one other thing I want to talk to you about, and that is only polar bonds absorb IR. You have to have bond polarity. Remember bond polarity? Where you have two atoms, they have a different electronegativity. So they make a little dipole moment, right? A little positive, a little negative. You have to have that polarity for the bond to be able to absorb IR. Okay? So what that means is that oxygen to oxygen, like in O2 gas, that does not absorb IR because that's not a polar bond. Nitrogen and nitrogen, not a polar bond. Okay? Everybody cool with that? That turns out to be a good thing. If it weren't for that, then our atmosphere would absorb infrared from the sun, and the Earth and all of its gases and everything would have heated up and everything would have boiled away, billions of years ago. Okay? It's the fact that our atmosphere is transparent to IR because we get a lot of IR from the sun. All that heat, when you go out in the sun, you feel heat on you. That's IR from the sun. Okay? If it weren't for the fact that those gases were transparent to IR, the Earth would have already heated up to where it couldn't sustain life. Everything would have burned away. Okay. This is the problem with global warming, global climate change, is that carbon dioxide, carbon to oxygen bond is a polar bond. So carbon dioxide absorbs IR. So when we put it into the atmosphere, it starts absorbing that heat that's normally transparent. It just comes and bounces off the Earth. Instead, it comes in and gets stuck, and the Earth heats up. So if we put more carbon dioxide, Earth heats up more. Okay? Really, really simple, basic science of organic chemistry. All right. IR correlation table. So the good news is that people have been looking at the IR spectra of organic molecules for about 80 years now. This instrument was invented in the 1930s, 1940s. Okay. And so what scientists do is that, they put a molecule in, they look, they say, oh, look, it absorbs here, it absorbs here, it absorbs here. They write that down. Then they put another molecule. Okay. And eventually they see the patterns, and then they publish a table. And when we want to use IR, we just look at the table. So that table is called a correlation table. It relates the frequency of the light that's absorbed. It relates it to a structural feature in the molecule. Okay? And it's already done for us. You don't have to memorize it. You should always look it up. That's fine. That's what you're supposed to do. Eventually, some of them you'll just memorize because you look them up so many times. Does that make sense? Okay, so look. What is it we're looking at then? Well, what we're looking at in a correlation table is two things. First is, what are the atoms in the bond? I'm sorry, three things. What are the atoms in the bond? Second, what kind of bond connects them? Right? Because atoms is mass of the balls, right? And the type of bond is how strong is the spring. And then the third thing is what type of vibration, because remember, we have stretching, but then we also have bendings. They work a little bit different. All right? So you can read through this. This is just generally reminding you of things. What I want to do is I want to look at the, I want to just make one point about the correlation table. The correlation table is a guide. It's not a Bible. Does that make sense? Like, in other words, it's not saying it absolutely has to be this way, right? It's saying these are the kinds of trends that we see, and we have to use some interpretation. Okay? In particular, what we see is that while I talked about the balls and springs, there are other things that can affect the way that things might vibrate. One really good example, one that you're going to see, is that you have C double bond O absorption. And the C double bond O absorption we're going to see on the table is usually slightly above 1700 for a frequency. But if we take that C double bond O and we put it adjacent to another pi bond, like a C double bond C, where we go C double bond O pi bond, then we go a sigma bond, then we have another pi bond. We're alternating. We call that conjugation. And we're going to talk about that in second semester in more detail. But one of the things that conjugation does is it weakens the C double bond O. Makes that spring weaker. Remember I said when the spring is weaker, the frequency goes down. So if the frequency was 1700, we make it weaker. Now it's going to go into the 1600s. Okay? Does that make sense? And so very often, for example, we will see a C double bond O vibrate at 1685 because it's conjugated with a benzene ring. Okay? It's next to a benzene ring. All right. let's look at our correlation table. Let me describe this for you really quickly. This is, I modified this a little bit from the one that was in your notes last semester. Oh, somebody just asked me, so V0 equals V1 if the speed is constant.
Oh, that was from the potential energy graph.
Yeah, no, I totally get what you're saying. Okay, so here's the deal. The amount of energy in V0 and the amount of energy in V1 is different. Okay? The potential energy is different. That means that they vibrate to larger distances. Okay? But the frequency is actually a constant. The frequency, the time that it takes them to go from here to there and back is a constant. But in order, obviously, since you're moving a larger distance in the same amount of time, at the bottom, they're going to be moving faster. Does that make sense?
Yeah, thank you very much.
So that's how that works. It's a weird thing. If I had someday I'll show you a little thing I can do to show that. Anyways, okay, so here's our table. I've arranged the table according to the frequency of the vibration, because here's what's going to happen. You're going to have an IR thing. You're going to look, oh, there's a peak here. Here's the number, right? That's what you're going to know. So you're going to start on the left, find a number. Then you're going to look at what kind of bond could that be? What would be in the bond, like a sp3 hybridized oxygen, sp2 hybridized oxygen, and so forth, right? And then finally, I put a little bit of information about the peak. Some peaks are really broad, some are sharp. And then there's also an issue about, the peaks are upside down. I'm going to show you some examples in just a moment. But if the peaks go down a lot, we say they're strong, which is S. And if they only go down a little, we say they're weak, which is a W. And then in between strong and weak is medium. Okay. And it's not perfect because also, like our particular IR instrument zooms so that no matter how big the peaks are, it makes them big. Does that make sense? So if you had all little weak peaks, they would all look like they were strong. So it's a little confusing, but anyways, let me show you. Last thing I want to do, I'm going to go through these really quickly, guys, because I know it's gone on for a while and you guys have been really patient, and I know it's boring to listen to me talk all the time. This will also be posted, okay? And I'm going to turn you guys loose in a minute, but I put some examples in here. And there's also more examples in the textbook, in the reading. And I highly recommend you look at these, because really you're going to learn by looking at specific examples. And so, for example, you guys have seen IR spectra already. You've seen what they look like. But, we see these peaks right here on the left. These look really big. And the reason for it, again, is because really normally they would be kind of medium or even weak. But there's no really strong peaks in this, so it blew them up to full scale. Does that make sense? But at any rate, see these peaks here? These peaks are what CH stretches look like. There's usually more than one. They all come together in a group, okay? Technically, they're sharp, but because they overlap, they just look like a blob with points on the top, okay? We also have, in this example, CH bending peaks, which there's usually two. It's like 1450 and 1375 or 1360. They're weaker. They're sharp, but they're a lot weaker. Sometimes you don't see them. Sometimes there's a lot of garbage on them, okay? If we look, you can see here's a C double bond C stretch. This here is the CH for the sp2 hybridized carbon, and then there's sp3 hybridized carbon CHs. You can see that when you go to an sp2 hybridized carbon hydrogen, the bond is a little shorter, it's a little stronger, vibrates a little higher frequency. Okay? And then we get other kinds of peaks like this. Okay? This is probably a harmonic overtone of this really big peak. This is out of plane bending of the CHs. of the double bond. So the double bond is flat, okay? It's flat, and then the hydrogens vibrate up and down like this, out of the plane, okay? And you can see that's a really strong vibration. And then it turns out, if we look at the frequency, that frequency is just a little bit above 900. Do you see that? What is that? Probably about 915. Okay, everybody cool with that? So it turns out that these vibrations, they work like the vibrations of a string. And I don't know if you're familiar with the vibrations of a string. Like you take a string and you pluck it and it vibrates. It has one main vibration, and then it has what are called harmonics, where in whole number ratios, the string vibrates. Like if you take the string, one is the whole string vibrating, then the second one is half the string vibrating this way, half the string vibrating this way. That's at twice the frequency, and then there's one at 3 and so forth, okay? Those are called harmonics. The main thing about harmonics is that they are approximately whole number multiples of the original vibration. So if you look, here's 915, look at here, do you see this? That's 2 times 915, it's a harmonic. I hope that makes sense, but. So that second vibration is caused by the first vibration. Do you see? We see these very often if there's low frequency, really strong vibrations. Do you see? Here's another harmonic. That's the 2 times 1000. Because look, see here, here's the 1000. Does that make sense? So that's why the IRs start to look really complicated. But what we're going to do is focus on the ones that we can understand, okay? All right. I want to show you, this is an OH. Most OHs of alcohols, I'm going to just make that distinction. OHs of alcohols, they come right around 3,300 or so. It's a little bit above it. Do you see that? Where the highest part is, just a little bit above 3,300. Okay, and they're very broad. You know, so it's really wide peak as opposed to like this peak over here, which is really narrow, right? Broad, narrow, sharp. Amines, nitrogen and oxygen are almost the same weight. Okay, and their bond strengths are a little bit different. And so the nitrogens come in almost, NHs come in almost the same place, but with NHs, you get a sharp spike. And usually you get, if it's got one hydrogen, there's one spike. If it's got two hydrogens, there's two spikes. Okay. Here's an aldehyde. Do you see? Here's the C double bond O of the aldehyde right there. Do you see that? And then look, this is at 1720. So 3,400, almost in 40. It's a little bit less. That's the harmonic. Do you see it? 2 times 1700. This is a carboxylic acid. Carboxylic acid has an OH. But the OH of a carboxylic acid comes at a lower frequency. Do you see? It's centered about 2,900. But do you see? It's this whole thing. It's super broad. Okay? So do you see how that looks different from the alcohol one? The alcohol one would be more like this. So we can tell the difference by the frequency, the shape, and its location, right? And finally then, this is an amide. If you look, an amide has that NH2. See? NH2, so 2 peaks. Close to where the alcohol is, little bit lower frequency, sharp peaks in it instead of one big broad peak, okay? And then here we have, this is actually the C double bond O. And I'm going to be honest with you, I can't remember why there's two of these. I think it might have to do with whether it's hydrogen bonding or not. I'm not even sure. But amides have resonance. It weakens the C double bond O. So because it's weaker, it goes to a lower frequency than your normal C double bond O. All right. Okay.